Right. Hi, everyone. Welcome back. Welcome to the keynote session. So in this session, we'll have Professor Tamsin Edwards from King's College London speaking to us for the keynote. Tamsin is very well known for her work in climate science. She's a professor of climate science at KCL, expertise in lots of areas like uncertainty quantification, particularly ice sheets and glaciers. She was one of the set of lead authors for IPCC AR6. She's very well known for work also in kind of public communication of science, with her fantastic blog that's very well known, and work with BBC and Guardian and so on and so forth. But I have a small personal story which you don't know about for my intro, which is that so this is the 4th year that we've run the summer school, ICCS summer school. I just remembered this morning that back when we did our very first summer school 4 years ago, I had really wanted to invite Tamsin to be the keynote speaker, but I was kind of too intimidated and a bit shy about it. So there's a lesson there. Even people further on in their careers do get shy as well. But then I met Tamsin at EGU last year in 2024. She gave a fantastic talk and we chatted afterwards, and I was like, oh, she's so lovely and approachable, and it kind of broke the ice for me. And then I thought, okay, I really got to get her at the ICCS summer school. So really glad that I could finally do that. So thank you very much for saying yes and coming. So over to you, Tamsin.
I'm so embarrassed. I sort of try and spend quite a lot of time like trying to become more approachable because I think it's all that hierarchical stuff in academia is a waste of time. So I'm really sorry that.
No. I'll give a better entirely myself. Yeah.
Also, you've embarrassed me about my blog, which has got no new posts for a really long time, but I do mean to come back to it at some point. Yeah, thanks for the invitation, and I hope thanks for having me. So I'm going to be talking about the IPCC that Dominic mentioned. Hang on. Let me just get used to this. So a couple of the kind of biggest things I've done, I guess, is this is a picture from the first lead author meeting of the IPCC 6th Assessment Report, Working Group 1. We're in China in 2018. There's a person in there with really bright blue hair. If you look closely, that was me. And then with less bright hair, this was a parliamentary event I did while an advisor to the UK Parliament in a sort of pilot role for 18 months that finished last year. So there's Ed Hawkins there, there's the head of the IPCC, Jim Ski, is in there. We did a panel event for MPs and peers about the IPCC. So, it's traditional in a keynote to sort of like maybe give a bit of your kind of career sort of retrospective, but I think you don't need to hear all that. I thought what you might be interested in is some photos of my equivalent summer school. So this is me as, I think, a first year, maybe second year PhD student. You can see, although I did particle physics as my PhD, high energy physics, and it was just about that. You can see that it's 2002, but we were still firmly in the 90s, judging by the curtains haircut on this guy, and his dancing style, and I'm even holding a CD. So just to show, we all start in the same place, I guess, is the point of showing that, and also to wish you lots of fun as we had at our summer school dancing and the like. So the talk is going to be in 2 parts. I'm going to kind of do a looking backwards to the last IPCC report for the first part, or sort of 2/3, and then I'm going to look forward ahead to the next IPCC report. This is another author meeting photo. The bright blue hair is over there. So I'm going to talk Working Group 1 report and the sea level projections in that. So this is our chapter team for the Chapter 9 Oceans, Cryosphere and Sea Level Change. And if you open the cover of the report and go to the summary for policymakers and you flick through a few pages, you get to some of these kind of global time series graphs. And I'm going to talk mostly about this one, which is sea level change to 2100. And then I'm going to mention this bar here, which is sea level rise in the year 2300 on the same scale. There's also an associated NASA sea level website, at least at the moment, which has all the regional sea level projections. So we propagated this to the regional. So as I say, I'm going to focus on this graph here in the summary for policymakers. The sea level projections to 2100. So I'm not going to focus on that high line there, which comes from a sort of expert elicitation study, but on the 5 shared socioeconomic pathway projections, 5 lines with some shading, and basically how we came up with those. And if we quickly look here, the sort of scale here is kind of 0.5 meter to nearly 1 meter of sea level rise from pre-industrial to 2100, which doesn't sound like a huge amount, but has an incredibly disproportionate impact on extreme sea levels. So under that second to lowest SSP, hopefully you're familiar with the SSPs, but the sort of 2 degrees warming type scenario, 126, if we have a sea level change of about 60 centimeters, then extreme sea levels that are currently seen once per century at the moment, on average will become 160 times more likely, and that's just on average, so in some parts of the world more than that. And under the highest emission scenario, the very high emissions greenhouse gas emission scenario, nearly 1 meter of sea level change, over 500 times more likely. So really enormous effects on coastlines around the world and coastal flood risk. So I know you've come from all different kind of backgrounds. If you're a bit hazy on sea level rise, haven't thought about it, there are lots of different components. It's not just melting of ice sheets and glaciers. There's also thermal expansion as the oceans warm, and a bit of a contribution from changing from land water storage going into the oceans. And all of these, again, something that people often don't think about if they mainly work with global climate models is each of these is modeled separately. And I'm going to be focusing mainly on, as Dominic said, glaciers and ice sheets, because these are the parts that I study, that I work with the modelers of. So we have an example model of Greenland here. There's an example model of Antarctica, and there's an example model of a New Zealand glacier here, and then the thermal expansion is coming from the climate models and the land water storage separately. So this is all done sort of piecewise, ground up, if you like. You can do kind of big picture ones, but this is the physics-based ground up is what I'm going to be talking about. And then the glaciers that I mentioned are typically divided into 19 regions around the world. So when we think about land ice, that means we're thinking about the 2 ice sheets, top and bottom, and those glacier regions around the world. And that's important because I'm going to be referring back to that 19 number in a bit. So just a quick sort of overview of the steps, and then I'm going to go through them. So we need to start with a bunch of model simulations of those different glaciers and the 2 ice sheets. I can explain where those come from. I'm going to be talking about emulating those, mimicking the simulations with statistical methods or machine learning methods. I don't know if you're familiar with those. I'll give a bit of an introduction, and I'll give a bit more technical detail for those who are already familiar. So I'll explain this wiggly diagram in a bit. And then with these emulators, which are mimicking the expensive computer models, the fast statistical methods that are mimicking the computationally expensive computer models, we're going to predict sea level rise and come up with a time series for sea level rise. So the point of the emulators is, as I say, fast statistical approximations, machine learning approximations of these simulations that can take days, weeks to run, not as expensive as climate models taking months to run, but still significant. You can't run as many simulations as you'd like. So you do some kind of statistical model of the behavior of that simulator so that you can explore the uncertainties more thoroughly. So I'm going to kind of go through that. And also potentially to predict for more scenarios. So maybe you could only do computer simulations under 2 emission scenarios, and this allows you to maybe interpolate to predict for the other ones in between. Okay. So starting with the glacier simulations, these come from the big model intercomparison project targeted at informing the IPCC. So when you've got ISMIP for coupled models, hopefully you're familiar with, this is the glacier model MIP. And so that's led by Ben and Regina here. And they were using the old emission scenarios, RCPs. And when you model the glaciers of the world, you do all 200,000 or so individually, separately, which is kind of amazing. And then if you sort of take one set of global glacier predictions as a simulation, we had getting on for 300 of those, which are coming from 11 different glacier models participating in the project, driven with forcings from about 10 different climate models. So across these RCPs, there were multiple climate models used, as I say, and the 4 RCPs. So that's the glacier simulations that I was working with. And then the ice sheet simulation similarly came from the ice sheet model intercomparison project, ISMIP, led by Sophie Nowicki, and then the Greenland parts and Antarctic parts led by Heiko and Helene there. So again, similar kind of numbers, around 300 simulations from around 14 ice sheet models, again, driven with lots of different climate models, because you have your climate model giving you your climate scenario as an input to your ice sheet model, basically, or your glacier model. They were only able to really run for 2 RCPs. They ran a few for the 2 equivalent SSPs as well, so high and low emission scenarios, basically. So this is all my data that I've got, kindly given to me by all these modelers around the world. And then this is what I want to do with it. So the sort of introductory bit, I want to quantify uncertainties for the predictions from these models using probabilistic machine learning. So kind of breaking that down, the idea is I've got predictions of the sea level contribution, say by the year 2100 from, say, Greenland. And I've got simulations at different levels of global warming by the end of the century, maybe under 2 different RCPs, or 4 different RCPs, the emission scenarios for the glaciers. So this is just a schematic, obviously, but I've got, and I've got multiple models giving me data points on this graph. But you can see it's still kind of, this is a schematic, but the idea is it's relatively limited because these simulations are not only somewhat expensive, but computationally expensive, but the modelers are doing this essentially in their free time. This is a sort of a voluntary project. It's not a funded project. So the MIPs tend to be sort of done alongside other work. So what we want to do is use machine learning or some kind of statistical method here to interpolate so that we can predict for any level of global warming. So in other words, any scenario, different scenarios that we used before. And the nice thing about the machine learning is it's going to give us kind of flexibility in that interpolation. We're not going to be saying, well, I think it's linear or I think it's a polynomial or whatever. It's giving you that flexibility. You're not presuming what the shape of that curve is. And then I'm going to talk more about this, but probabilistic, basically multiple different curves, multiple different ways of interpolating to think about the uncertainties in that interpolation. So the uncertainties in the machine learning. And so again, just to reiterate, the sort of point of all that is to predict sea level contribution under lots of different alternative values of the global warming, say by the year 2100, and I'll come back to more detail on that, but say by the end of the century, for any scenario. Of course, each scenario has uncertainty on the global warming. Say if you have high emissions, greenhouse gas emissions, you have uncertainty in the global warming for that scenario. So you have a spread of values. And also here we're going to show different ice sheet model parameter values. So if we can capture this picture as a function of not only global warming, but also of these ice sheet model parameters, then when we're happy with our machine learning model, we can explore any global warming value and any value of the ice sheet model parameters to predict what the sea level contribution would be. And then you can generate, thousands, tens of thousands of realization because your model is so fast, and you can get a better picture of the uncertainty of the probability distributions for sea level rise. Okay, hopefully that makes sense. So that's the sort of overview of the method. Technicalities, if you're interested, I work with John T. Rougier, who's a friend from when I used to work back in Bristol, in University of Bristol. If you're not familiar with Gaussian process regression, this is a nice demo website. You can click around with different settings and see what it does, which I've used to generate the schematic. So the idea is it's just, it's a type of regression, and it's nice because it has this flexible property. It's non-parametric. You're not saying I think this should be a linear relationship or a polynomial. You're saying, please find me what this relationship is, perhaps given a certain level of smoothing. And the nice thing about Gaussian process, the reason they have been very popular for a long time, kind of before people started calling it machine learning, it's the sort of old school probabilistic machine learning, is that it gives you these uncertainty estimates. So in this picture here, we've got maybe, so for example, if this input was global warming, like I showed before, and the output on the y-axis was sea level contribution, we've got a handful of simulations as the dots, and our Gaussian process is giving us a mean interpolation through the dots, a mean function, and it's also giving these big loopy uncertainty intervals for the gaps in between the simulations. And so the way that you do this, you make it kind of go through the points, is to set something called a nugget in this Gaussian process to 0. Basically, it just means that it passes through those points. So this is the kind of classic way that a lot of people in uncertainty quantification will try to quantify uncertainties for expensive computer models. They have a Gaussian process emulator of their simulator, and they make it pass through the points, and then they can use the emulator to predict anywhere along that line, and then in any other dimensions that they're doing the same thing, right? So different parameters usually. Robust GASP is a sort of relatively well-known one that I've been using in R. This kind of thing, often they work quite well out of the box. I've put a few details here for people who are interested. I don't need to go through all of them. I will mention that there ended up being rather a lot of emulators, 2,000, because what I do is I create one of these for each of those land ice regions that I mentioned. So the 19 glacier regions that I mentioned, Greenland, and then I split Antarctica into 3. And then for various reasons, which I can come back to, I emulated each year individually. So I had an emulator for the sea level change up to 2020, 2021, 2022, 2023. And mathematically, that was easier to do. But as you'll see, it was a choice I've revisited in my current work. It was kind of a bit out of necessity. And the kind of key thing I want to sort of highlight here, the sort of slightly unique or unusual thing, I guess, about this analysis is that because we've got a multi-model ensemble here, we've got multiple realizations. You can see there's a stack of dots at each point here, like I showed before. Then there's no kind of single point we want to pass through. So we allow this nugget term. This is basically a kind of tolerance here that allows the emulator to treat these as noisy observations, as noisy simulations, basically, like as if you had a stochastic simulator with lots of different possible output values, some kind of uncertainty here. So you can set this nugget term to be estimated so that it can sort of have that flexibility to go through multiple points, basically. And there's some kind of assumptions for that. You have to assume that the models are kind of independent enough to do that. And actually, ice sheet and glacier models were quite lucky. They're more independent, I would say, than global climate models. And another key thing is you need these models, of course, to all kind of sit on the same axis for the emulator to sort of be able to understand those relationships. So you need the models to vary some common inputs. They don't necessarily have to have the same values of those. But for example, we've got global temperature of the climate model they've been using. All of the models have to be driven by a climate model, and so we can use that as an input. And as you'll see, we were lucky enough to have a few other inputs that were varied across all the models as well. So this is kind of what's weird about my use of emulation for models. It's trying to chuck the whole multi-model ensemble in at once and use this nugget to deal with the sort of noisiness of that. And this has been done before for other similar applications, but I think maybe not for multi-model ensembles that I know about. And so this is kind of now looking at the actual graphs from the paper. So this is one of the glacier regions from GlacierMIP 2. So we've got similar kind of thing. We've got global temperature change up to the year 2100. We've got sea level contribution in the year 2100. We've got simulations from all those glacier models under the 4 different RCPs. So as it gets warmer, that contribution increases. And then the curves are the emulator. Again, like I showed before, we've got a mean line through here, and we've got an uncertainty range here, which is what we like about the Gaussian process. So that's one example for the Antarctic peripheral glaciers, kind of around the edge of the ice sheet. And then I won't kind of go through these in detail, but just to show a kind of a principle is for the ice sheets, we've got Greenland and I've got West Antarctica. Remember, I split Antarctica into 3. Similar kind of idea. This is sea level contribution at the year 2100 against temperature change. And again, as you go from the low RCP or SSP scenario to the high, you get a greater sea level contribution, and the emulator is then capturing that relationship. West Antarctica, there's actually not a very strong temperature dependence. But what I really wanted to highlight here is that we've got a parameter for each which has been varied across all the models, which again is unusual. It's unusual for models to be changing the same parameter in a multi-model ensemble. And it doesn't matter too much for our purposes what these are, but I've put these here. They're basically the sensitivity of the ice sheet to the climate forcing, the ocean warming, for example. There's a kind of parameter that drives how sensitive it is. So as I say, this is kind of unusual to have this. There was another kind of parameter or ice sheet uncertainty that was varied in Antarctica, which was a sort of ice shelf collapse scenario. You can read the paper if you're interested to find out more about that. But just to show just a quick diversion on sort of the probabilistic aspect of this. Oh, hang on. So what I see very often when I go to conferences, including EGU last year, I see lots of people like adopting machine learning enthusiastically, which is great, but often showing using machine learning methods that don't quantify uncertainties in their predictions. And that might be because their data sets are very, very big. It might be because it's not a priority for them. It may not have been specified to them as a thing that has to be done. But I just want to get on my kind of polemic sort of standing on my soapbox for a second, because if you have an emulator that you're comparing how well it does at capturing your simulation. So this is the result of a leave one out validation, where you leave one of your simulations out and then you try to predict it with your emulator and see how well it does. So you want all your dots here to be along the line of equality. If you look at just this with the dots, and you haven't got any uncertainties on your emulator, on your machine learning, you think, great, my correlation here is 95. That seems pretty good. Like everything looks good. If you look at the, this is a real example of mine. If you look at the equivalent when you plot the error bars of your machine learning in a Gaussian process, where you want these error bars to be crossing the line, you can see that actually here we've got a red value here of 84%. And that's saying that only 84% of these dots kind of cross the line, the error bars cross the line, but the error bars are 95% intervals. So we would expect a good emulator to be hitting the line 95% of the time, not as low as 84%. So this is suggesting that the emulator is actually a bit overconfident. It's got quite a lot of misses. But most importantly, if you don't have these error bars, you can't include the uncertainty in your emulator in your predictions. So it's not only is it a kind of incomplete validation, we can't test whether the emulator is overconfident, but we can't capture the biases and the uncertainties of our emulator in the predictions. And of course, when we're making predictions as important as climate change, I would argue that's completely essential. We wouldn't expect to do any science without error bars, whether it's experimental, whether it's thinking about climate model simulations, or whether it's thinking about the machine learning of those climate simulations. So I think this is really essential. I think it's something that's only started to be realized as really important in the machine learning community in the last few years, as I understand it. But I do agree with Amy McGovern saying we should be using uncertainty quantification in machine learning routinely. It shouldn't be a sort of special interest. So we can do these leave one out validations. I'm not going to go through this, but in the paper, you do all these plots and you check everything looks sensible. You check the coverage is kind of around 95%. You check there aren't any huge biases on your emulator. And, you know, it's not perfect, but considering the kind of noisiness of the data, we decided it was they were adequate. And then we basically propagate our uncertain inputs through the emulator to make the predictions. So we have distributions for our global warming change in the future. These come from a fast climate model. We have distributions of global temperature change for the different modern emission scenarios, SSPs. And then we've also got those ice sheet model parameters that I mentioned as being uncertain. So we've got Greenland and Antarctica. We have a couple of parameters for those. And those have distributions that have come basically from the modelers. So when we sample from all these distributions with the emulators, we generate, you know, tens of thousands of realizations, say, exploring all these different combinations of the uncertain inputs. And importantly sample from the emulator uncertainties as well, then we can come up with some sea level predictions. So that's what we did, and that work couldn't have been done without all these collaborators, incredible number of modelers and other experts helping with this. But again, that's the sort of overview of the paper if you want to go back and look. But we came up with these land ice projections for sea level rise. And the GitHub's there if you want to have a look. So that's the sort of land ice part, but what I showed before was global mean sea level. I mentioned there are other contributions than land ice. So what we did to combine with the other contributions, the thermal expansion and the land water, is put it into this framework called FACTS. Again, you can read more about this in Bob Kopp's paper in Geoscientific Model Development. Basically calculating that total sea level change, recalculating it for the IPCC using the latest temperature projections. So the IPCC can do new calculations, but it has to use published methods. So we publish the methods, and then we combine them together in the IPCC using all the latest global temperature projections. And that's how we came up with these 5 SSPs. So far so good, and that was kind of more a big project than had been done before in this area. But inevitably, no research study is ever perfect. There's always things you wished you'd done differently or would do differently in the future. So thinking about the year 2100 projections and my, the land ice ones that I led, although it was great that we had these ice sheet model parameters to explore and kind of very new and unusual, there's still not very many. There are plenty of uncertain parameters in models. That thing I mentioned about emulating each year independently was a bit of a shortcut and was a bit hard for people to use and interpret the results. And also, I've not mentioned at all evaluating all of this with past observations to see how well it's doing. And this, just quickly coming back to the 2300 bars, the sea level change in the year 2300, this was very kind of back of the envelope, really, because there were not many studies out there to use. Especially not physical simulation studies. So there was a lot of like extrapolation, expert judgment, kind of interpreting RCPs as SSPs, even though they aren't the same thing. And so we just basically said, well, we're just going to give a range. We're going to say it's low confidence. We're not going to give a full time series. So this is really like a big information gap for long-term sea level rise. Anyone who cares about that for coastal vulnerabilities, nuclear power plants, this kind of thing. As I say, and coastal flood risk, I mean, this is potentially, we're talking meters of sea level rise as being an existential threat for small islands in particular. So I want to talk quickly about how we are attempting to make the next round of predictions more robust, more useful, trying to improve on those things that I just mentioned on the previous page. With a view to basically, hopefully, publishing papers, improving the FACTS framework tool that I mentioned, so that it can be used in the next IPCC report. So the first half was a bit more keynotey. This is the big thing I did in the past. This is more seminar. This is like very work in progress. Love your feedback on it at the end if you have some. So we had a scoping meeting for the 7th assessment report in December. And that's just a picture of us there, just to introduce the fact that I'm going to be talking now about the next report. This very preliminary work, as I say, lots of people involved. This is all done under a particular funded project this time, the EU project called Protect, which is led by Gail here. So lots of institutions across Europe, various stakeholders from around the world, like Greenland and the Maldives. Lots of people helping, including Johnny, who is here this week, basically to predict sea level rise for the next kind of round of projections. So kind of some of the ways that we've tried to improve or have improved on the last analysis that I showed and the last MIPs that I showed. Longer term, so instead of going to the year 2100, lots of our simulations go to 2150 or even 2300 under different shared socioeconomic pathways, so the SSPs, the new generation instead of the old generation of scenarios. And you can see that compared with the previous MIPs, this isn't an international model intercomparison project, it's an EU project. So we have fewer models, we have sort of 2 to 4 models instead of more like 10 to 15. But we have many more simulations and, as I'll show, exploring many more modeling uncertainties. So we've got larger ensembles to the year 2150 than 2300. Not every model can go as far as 2300. But the number of simulations we're talking about here is more like 1,000 per ice sheet or glacier region, as opposed to more like 300. And as I'll show, that number is still changing. And so I wanted to sort of talk about some of the behind the scenes stuff around experimental design and uncertainty stuff that that was quite unique to the project and that we learnt a lot from. So one of the things was we provided kind of ensemble design guidance for our modelers. Now, remember, we're not just working with one modeler, which is maybe more common, but lots of modelers spread all across Europe, looking at both ice sheets and the glaciers too. So we kind of gave guidance on which scenarios to use. For example, thinking about the high and the low scenarios so that we can interpolate between the two instead of extrapolating. Trying to use the same GCMs and scenarios across Greenland, Antarctica and glaciers, because these are slightly different communities. Going back and simulating the past so that we can compare with observations. That wasn't possible in the previous analysis. And then when we think about experimental design for the ice sheet and glacier model simulations themselves, their model uncertainties, again, we need them to vary some of the same parameters, some of the same choices as each other, so that the emulator, the multi-model emulator, can kind of link them together and understand how their relationships match up with each other. And then this is sort of standard experimental design stuff. You want to explore your uncertainties widely. Latin hypercube is a nice design. Categorical inputs are a pain to emulate sometimes. Don't change your parameter values from the historical period to the future. We found some people doing that because then it means you can't evaluate those parameter values using observations. You can't calibrate. And a sort of iterative design, like don't blow your whole computer budget at once, but save some for as we learn as we go. We think, oh, I wish I'd done some simulations there. I'm going to add those later. And I guess what I wanted to say really is it's not even though technically I was in charge of their experimental design. In practice, right, this is like herding cats, isn't it? Trying to talk to academics and modelers who have their own expertise and their own opinions, and quite rightly, about their models and what they want to do. There's a kind of a limit to how much you can really say, here is what the design should be. So you try to give this guidance, you try to sort of persuade people why these principles are important. Sometimes the modelers didn't follow the guidance and we had to add or rerun simulations, but we all still got on at the end of the project, so that's the main thing. And it just shows how complicated this stuff is across big projects. Just to show sort of an example, so the sea level time series that we get from those, we've got lots and lots of simulations. You can see by the faint lines for Antarctica, Greenland, glacier regions, going up to the sort of century or so timescale, the year 2300. Again, I want to sort of focus more on methods here than results because it's preliminary, but just to show you what those ensembles look like. And I'm not going to go through this, but this is to indicate quite how many uncertainties we explored. It was a lot. So it wasn't just parameters. We've got different model structures, different parameters, different initial conditions or initialization methods, and different boundary condition sort of types and categories. So for Antarctica, we had 22 different uncertainties explored across the ensemble instead of 2 in the last analysis. For Greenland, we have 9 instead of 1, and for the glaciers, they didn't perturb any, they didn't vary any parameters, so we had 8 compared with the previous, which was 0. So all these different colours and rows and things give all that detail, and you can ask me about that if you like, but basically a lot. And I wanted to just quickly go through, again, this is a bit more of a technical point of just behind the scenes stuff. If you want to emulate multiple models at once, and you have to kind of put them all in the same data set, the same spreadsheets and the same rows and columns, you have to work out how those models relate to each other. So if you have like a drag coefficient for something in one model, does it have the same meaning as the drag coefficient in another model? And therefore, can you put those values in the same column? Or is it actually defined differently? You've got to maybe transform it or call it something different because actually it has a different physical meaning, right? So that's the really hard part about multi-model emulation, is working out those relationships between the models. It doesn't have to be perfect, but it has to be good enough. So this kind of translation between the models, things like I said, definitions, units, transformations. Sometimes you have things with the same name, but they mean something different and vice versa. You have to kind of have values in every row and column of your spreadsheet. So you have to sort of put values in that don't exist in the model, you know, that aren't actually, the parameterization doesn't even exist in that model. And all of this requires a lot of talking to all the modelers, a lot, over and over again. Now, what does that mean again? Is it the same as this? Is it different from this other person's model? Delving into the model equations, do you understand the physical modeling enough? And that takes a lot of relationships, a lot of trust, and a lot of time, just constant communication to get all the kind of bits of this lined up. So again, this is kind of now similar to what we did before. We're going to have this multi-model emulation like I showed before. I'm emulating the 2 timescales separately because I've got quite a big ensemble to the year 2100 or 2150, depending on whether you're talking about ice sheets or glaciers, or the year 2300, we've got a smaller ensemble. I'm now emulating the whole time series at once instead of each year independently. So that's using principal components. You can ask me about this if you're interested. All of those millions of uncertainties we explored, they're all explicitly put into the emulator so that you can sample them later. I'm just doing Antarctica in one part for now. I'm just using a subsample of 1,000 simulations because that's all my Gaussian process can cope with. I'm going to come back to that. I have got a few extra details here, but if you want to ask me more details about the analysis, perhaps we can have that in the questions. I want to carry on. Leave one out, validation, just like before. This is all the preliminary analysis we did last year, actually, that I showed in EGU for our kind of project deliverable. I'm going to show how this is changing still. But for the preliminary analysis for the project deliverable, we had 42 emulators. The coverage looked pretty good for most of them. Again, I'm not going to kind of go in fine detail through these, but this is the kind of check that you do across all your emulators to check that they're sensible. And then, just like before, we want to propagate our uncertain inputs through to the end with our emulator. So just like before, we've got distributions of global temperature for each SSP. Here's a couple of them here. And just like before, we have distributions on our model parameters, except now it's not just parameters, it's structure, it's initial conditions, it's boundary conditions, right? So we have loads and loads of uncertain distributions here. And mostly we just use kind of simple choices for those. And again, adding the emulator uncertainty in as well to make sure we don't underestimate our uncertainty. So again, I just want to sort of mention, not in great detail, but just the fact that we're now able to evaluate all of this with past observations. So we're using a Bayesian calibration. Basically, if we look at an example here for Antarctica, from the year 2000 to 2020, this shading here is the emulated projections. So going from the past through to 2300 or whatever. And the shading is the kind of, I think it's the interquartile range and the 5 to 95%, something like that. And so that's the kind of raw emulator projections when we've sampled all of our global temperatures and all of our ice sheet model parameters and everything else. And then this calibrated here, note we've zoomed right in an order of magnitude on the scale here. This is after calibration, where this is my kind of target observation, which has come from satellite data. So this is the uncertain kind of trend over 20 years of the ice sheet mass loss, the ice sheet sea level contribution. So the kind of target is this kind of cone here. And after calibration, we've basically downweighted everything that's outside that range. You can see the range is actually just about visible here. We've downweighted all the tails each side of that, and we've upweighted everything in the middle to constrain the uncertainties in that Bayesian calibration. So again, if you're not familiar with that, you can ask more, but basically the idea is to squish our projections so that they match the observations in the past, and we give greatest weight to the predictions in the future that were best in the past. And so again, if you're kind of familiar with Bayesian calibration and model uncertainty, this sort of big bar here, it includes the observation uncertainty, and it also includes a term for model uncertainty called model discrepancy, which is an uncertain part of the analysis. And very interesting, and I could probably do a whole seminar just on that alone. But I will continue to say we basically now are putting this into facts. It's already in facts in a kind of preliminary. So it's already in facts with the help of the same people, Bob Kopp particularly, predicting to these longer time scales. I'm separating the building of the emulator from the predicting, which makes it all much faster. There's a few limitations still to figure out, like some simple extrapolations going on when we don't have the very, very preliminary results. So caveats apply. I'll show you why these numbers are probably going to change. But basically the global, sorry, the resolution's not very good. The global mean sea level projections, now we've got a full time series instead of just a bar at the end of the period 2300. We're using all these 5 SSPs instead of just 2. The numbers seem to be actually surprisingly similar to the AR6 bar at 2300, considering the methods are entirely different. So this kind of low scenario here, we're actually coming up with very similar ranges. The high is quite similar too. So the idea is that this is what we're aiming for once we get the final result, once we finalize the analysis. This was the first pass. What we have on the to-do list and why these numbers I expect are likely to change is since last spring, when I did this analysis and showed it first, we've now got 3 new model ensembles, and Johnny ran some of those simulations, and my other student, Meg, did a bunch more. We've got a new scenario or a new SSP, which is a sort of slightly more overshoot temperature scenario. And not only do we have a third more Antarctic simulations than before, but about 10 times more glacier simulations, reaching over 8,000 for some of those regions, mainly thanks to Meg. But this is great. This is great. Lots of information, lots of uncertainties explored. But also it means that my Gaussian process emulators are creaking at the seams and unable to deal with that amount of data. So I'm currently looking at sort of Gaussian process is adapted for big data and for these complex kind of relationships. I'm looking at deep Gaussian process and local approximations if you're interested, or if you have any ideas for me to try, I would love to hear it. As finessing the calibration to make it a bit more sophisticated and using new data. If you're sort of thinking, well, why am I sticking to Gaussian process? Here's a quick job advert. What about other types of machine learning? Just found out last week I've got funding for a one-year postdoc to basically look at this problem, same data, same aims, but using other machine learning techniques. We've already started to look a bit at random forests, but basically we want to try and hit this with other machine learning types. So look out. Please come and ask me about it if you might be interested, and look out for the advert. So that's all really just to summarize what we've been trying to do, improving our probabilistic machine learning emulation of land ice projections. I've gone through all these kind of improvements, longer time scales, more of everything, better of everything, hopefully, if we can finish it all, sharing it all in GitHub and Facts for these improved projections. And just my final thoughts, essential to have machine learning with uncertainties, essential to have good communication, working with other people, and a good sense of humor. And just to finish, you can change. This is to show that from these original people, I'm still very much good friends with these two women, and they both moved from particle physics into climate change, like I did, Climate Change Committee and NASA. So you can change direction in your career, and your early career colleagues that you meet in places like this, and friendships can last a lifetime and even through career changes. So I still work with these people on climate change, even though we started off in particle physics together. All right, thanks very much.